lecture of Professor Deepak Dhar on multiple transitions in rotors.
Okay, so let me start. So let me start with a sort of general comment. So this we have been studying, changes in the properties of a macroscopic system consisting of hard particles when you change the lattice spacing. And this problem is a little bit different than changing the volume of the system. It is supposed to imitate something like that, but it's qualitatively different. So one should think of the lattice spacing as a parameter. It does control the volume per particle, but there is a simple illustrative example for this, which is the following. Consider a one-dimensional Ising model, and there is a coupling, nearest neighbor coupling J. And so the partition function per site is 2 cosine hyperbolic beta J. But now I imagine that this J, which is the coupling, is a function of the lattice spacing A. So the partition function has some nice convexity properties with respect to beta and J, but not with respect to A. So J of A is a function which I'm allowed to specify any way I like. The allowed choices of J are not strongly dictated by any fundamental principle. Okay, so then the dependence of the partition function on A can be somewhat complicated, and there are no obvious convexity properties or other things related to the free energy as a function of A, while they are with respect to beta. So for example, in most cases, people often study things like square well potentials where J is a non-smooth function of A. And so if I use some such potential, of course, the free energy will inherit that jump in as a function of A. And so, that's the kind of stuff which one can have in such systems. And things like jump in the entropy as a function of A, which are not allowed by convexity properties here, will be allowed because A is a macroscopic parameter. When you want to say that entropy is a convex function, it comes because of the condition that if you have something like this, then there is a way to get higher entropy by breaking the system into two phases with different density or some such thing, Maxwell construction. But here the A has to be the same everywhere. You are not allowed to make one part with one value of A, one part with another value of A. And hence the convexity properties don't hold. Okay, so this is yeah. No. The thermodynamic limit exists in this system for each A, for each J of A. There is no problem. It's just that the dependence of the free energy on A is not strongly governed by some convexity property. For any particular value of A, the system is very well behaved, the entropy is well behaved, and everything is good. But it does not have, in fact, nothing is infinite either. But it is just that because A has to be uniform everywhere, you cannot break the system into two parts with different order parameter or some such thing, and convexity properties which depend on this kind of a decomposition don't hold. A is the lattice spacing, and I can imagine a case where, as I vary the lattice spacing, J of A is 0 here and non-zero here, and here it is finite.
thermodynamic limit does not exist.
Why not? Of course, it exists for any.
No, if it's a finite thing, it doesn't. Is Ruel's book?
No. So this is a lattice model, with Ising model with nearest neighbor coupling.
Okay, we'll discuss later.
Yeah, so everything, all limits exist, there is no problem. But as a function of A, the free energy can have very singular behavior, which depends on J of A, which is almost a free function. All possible values of J of A are not allowed. I don't want it to be minus infinite, then the limits will not exist. But otherwise, it is perfectly okay. Okay, the second comment I would like to make is that the reason some of these models are very interesting is that the couplings are effectively anisotropic. So this word is not very good, so let me explain what I mean. Suppose I consider a 2D model in which at each side there is a long rod and the spacing A is less than the length of rods, substantially less. Then if you put two rods nearby, then they are nearly parallel. They are not exactly parallel, but they are nearly parallel. Otherwise they overlap. But if they are like this, then there is more leeway per rod to flip. Then if they are more in the horizontal, they are like this. So this state is preferred over this. So, if I want to write some effective Hamiltonian, I will write that the spins can be either nearly along the x-axis or positive y-axis or negative x-axis, negative y-axis. Then this Hamiltonian is kind of described by something like this, minus sy, sy. So sy can be 1 or 0, sy squared. Okay, it can be 1 or 0, and 1 is preferred when they are in the x direction. Okay, but the coupling in the y direction will prefer the x orientation. So the Hamiltonian will be minus sy xy along x bonds and minus sx squared along the y bonds. So these kinds of couplings have been studied a lot in other contexts, like Kitaev model is a very well-known example of such couplings. And the reason some of these models become soluble is because the couplings are anisotropic, and coupling in one direction is different from the type of coupling in the other direction. And okay, so this is the so one can construct other variations, but the system we are studying is kind of natural in some sense. So we take hard particles of a particular shape and see what is the effective coupling, and of course it has this basic feature that it is anisotropic couplings. So now what I want to do is I want to just show. So in the previous lecture, taking care of vacancies, not self-averaging. Self-averaging occurs in any case. I think what the anisotropic coupling does is that the Hamiltonian has some structure which makes it easier to solve. Like if you take the Kitaev model, it has many more constants of motion than the Heisenberg model in 2D or some such thing, right? So, so it actually, I don't know in much better detail, but they have similar structure. And part of the reason these models become a bit more soluble is because of these anisotropic couplings, effectively anisotropic couplings, even though by definition we just had overlap condition, right? But the overlap condition is different really when you are like this versus like this. Okay, So taking care of vacancy, so what we had done in the tangent construction. So to recall, we were trying to construct S of rho as a function of rho, and there is a function which kind of looks like this. At rho equal to 1, it is finite, and we wanted to determine this function. We were actually able to determine some other function which kind of looks like this, which is S-nematic, which was fully ordered nematic state. Okay, and then we argued that in some region of parameters, these values are actually nearly coincident. So this graph has been drawn not very carefully. It kind of looks like this. Okay, so in some region, these curves kind of overlap and then they diverge, and that small rho also they will diverge, they will separate. But in intermediate regime, they are the same. And then we said there must be a tangent construction. And if we use the tangent construction, I tried to argue, but not a rigorous proof, that in some region, this answer is correct to order exponential k to the power minus k kind of stuff. But over here it is wrong, and over here it is wrong. Okay. And so here, when you make the tangent construction, what one says is that if you have a density like this, the system will phase separate into one part with density rho 1 and one part with density 1. And that is not good. And because, of course, at any finite rho, there is a finite activity. And if at finite activity, there is a finite density of holes, and do the holes mess up the whole argument? Okay. So to fix this, what we would like to do is we like to improve upon this construction and make a better estimate of the entropy in the high density region. Yes. The pre-regions which are not covered by the rods.
Yeah, and they are free to move around.
Yeah, so so we are not discussing dynamics, so I'll just say they can be at various places. Okay. So the way we do this, variational calculation of high density phase. Entropy. So to recall, in this intermediate region, we had used a fully ordered nematic state and calculated the entropy, and we were very lucky. The entropy was nearly exact with very small corrections. So now can I do the same thing in the high density phase? So we will set up a variational state which is exactly calculable. It doesn't count all the configuration, but hopefully enough number of them such that it gives you a fairly good answer. And those configurations will include configurations with holes. That is my aim. How do I do it? Okay. So the construction is like this. We define two kinds of tiles. There is a tile which looks like this. It's a 1 by k rectangle, and it is covered with one rod. There is another tile which looks like this. Yes. And it is covered by k horizontal rods. So it's a k by k square. And now I construct a long configuration by arbitrarily gluing together these things in some way. Okay, so I generate a set of fully packed configurations of a strip of width k, and then I can take all these widths k and make a bigger two-dimensional configuration fully packed. Doesn't count all the configuration, but hopefully it counts a fairly large number of them. Okay, So now just let us define a weight for this is called x to the power 1. 1 is the width of this, and we are just counting according to the width. And z is the number of rods I put in. So I put in 1 rod, z to the power 1. Here I put k rods and the width is k. So the weight is x to the power k, z to the power k. And if I put several of these things together, then the weight of a configuration is the product of weight of all the tiles which are used to make it. And the weight of a tiles are just these. And the weight of a configuration is z to the power number of rods, x to the power the width of the graph. Okay, so I will define omega of xz is equal to summation over all rectangles of all lengths, of all lengths, but width k, x to the power length of rectangle, z to the power number of rods. And this summation is very easy because, you know, each weight, this is equal to summation over n, w1 plus w2 to the power n. We usually sum from 0 to infinity, where length 0 is allowed, it gives you 1 in the partition function. Okay, so this is zx plus zx to the power k whole to the power n summation over n, which is 1 upon 1 minus zx minus z to the power k, x to the power k. So if I take this partition function and pull out the coefficient of x to the power L, it gives you exactly the partition function of full packings of that system. And, you know, so this part is very easy, but then you see that as a function of x, this function has a singularity at a value x star, and 1 upon x star is the partition function per rod in this full packing part. But now, suppose I don't do full packing. So we will add a configuration here, which is k plus 1, width and k here, and I will fill it with rods. So if you look at this partition function for any fixed z, there is a closest singularity on the positive real value of x, and that is called x star. And that, so this series will go like 1 upon x star minus x. So, you know, as a function of x, its power is x to the power L, coefficient is x star to the power L. And so the radius of convergence is when this is lambda to the power L, so it's x star is 1 upon lambda. So it gives you the partition function per rod, and that is what I need to determine the thermodynamic limit. And this gives a lower bound on the partition function because I haven't taken care of all the configurations, only a subset of them. Okay, but now I will add configurations with k rods, but in a size k plus 1, and each rod can be placed in 2 ways, either to the left or to the right. So the weight of this is 2 to the power k, x to the power k plus 1, z to the power k. Okay, and I do the whole calculation again. So omega is equal to 1 upon 1 minus xz minus z to the power k, x to the power k minus 2 z to the power k, x to the power k plus 1. You know, if you expand this, you get more configurations. The partition function per site is bigger, and the configurations include some number of holes. There is an extra feature, which is that you can start by taking some k vertical rods here and remove 1 rod, and then you create this extra space and you can slide the horizontal rods. So if you remove 1 vertical rod, you have actually 2 to the power k different configurations of horizontal holes available. So there is a lot of entropy which I can get by removing a rod. So I have taken care of this excess entropy of, effect of removing a rod gives you exponentially large number of configuration partly. I didn't take care of all the things, but I took care of a important fraction. Now I can take this series. Again, for each fixed z, there is a value of x. I will determine x star. And given that x star, I can determine the partition function per column or per site for this problem. Then differentiate with respect to z, I get the whole density, which is finite. And I can, study how this varies. And I will not do the whole calculation here. What one finds is that lambda is equal to, let's do that first calculation here. Let's stick to this one. So here, zx plus z to the power k, x to the power k should be 1, for the singularity, which is the same equation as what I got before. So zx should be equal to 1 by lambda plus 1 by lambda to the power k equal to 1, where lambda is 1 upon zx. And so you see that this is the same equation that we got before. And it gives you the entropy per rod, which is what we got before, which is asymptotically exact for the first order term. Okay. So now, if I do this, I get a correction to this. So the true big lambda, which is the correct lambda, is greater than equal to lambda, which was the where lambda is a solution of one upon lambda plus 1 upon lambda to the power k equal to 1. And it is greater than lambda 2 of z, where lambda 2 of z is a solution of this equation. Lambda 2 is equal to 1 upon x star, and x star is a solution of 1 minus x star z minus x star z to the power k minus 2 to the power k x star z to the power k plus 1 z star to the power k equal to 0. So, you can solve this and asymptotically and find the z dependent solution and see what is the density. And it turns out that density of folds is 2 by z, but z is actually k to the power k. So it's 2 to the power k over k to the power k order. It's very small for large k. So, my answer didn't change very much. Now, if I'm very ambitious, I can add extra configuration. I can also add, k plus 2 block and slide the rods more. And, then you'll get an improved bound. And fortunately, all these are systematically lower and lower in the corrections become even smaller. So one can systematically improve these bounds and get the correct answer to any order. And this basic picture remains. You still get the same two-phase region. Now, there is a region where there is a high density phase, and the coexistence doesn't occur at ρ2 equal to 1, but it occurs at ρ2 equal to 1 minus exponential minus k. So this part goes through. Okay. So that was about the K-MER problem. Now I want to discuss the transfer matrix, and the structure of the transfer matrix, and how this funny miracle of infinite number of zero eigenvalues occurs. Yes.
To what order is this calculation exact? It's not clear.
Yes, it is not clear. So, but what I can do is I can add these horizontal rods, tiles, and I can do this calculation. But I can also do this in the vertical direction. I can make a tile which is 1 by 2K with 2 vertical rods and do a similar construction here, which goes like this. So this is a full packing configuration where, this is with 2K and this is K by 2K. Okay. And, put the arbitrary concatenation of these tiles and see what's the answer. It turns out that if you do this construction, the value of lambda you get is bigger. Okay. But lambda is equal to 1 plus log K by K squared. This we agreed. But in one case, it is minus log K by K squared. Sorry, this is lambda to the power K. No, lambda by K. This is lambda per this is lambda per layer. So I think this is good. This lambda to the power K is 1 by, this is the partition function per column. And it goes like this. And actually the correct answer is that it's greater than equal to this. But in the second construction, you get it is greater than 1 plus log K by K minus 1 by 2 log K by K and so on. So, the bounds are not correct, but to leading order, they are the same. And if you put now vacancies in this stuff, you still get the same behavior. All that changes is that instead of, this 2 to the power 2 by K to the power K is what I wrote here. This becomes 2.7 to the power K by K to the power K or some such thing. So we don't know the exact value of the correction terms, but whatever improvement you make, they are always exponential in K. And so, we will just say that, you make as many corrections as you like, and some are more leading than others, and they are all exponential in K, and so perhaps the sum is also exponential in K. Okay. The exact asymptotics in K is a bit tricky, as I explained before, so, in some ways you have to get this log and how to cut it. And as we discussed this perturbation expansion about the nematic state. That's also somewhat problematic. What's the status of this? Because it doesn't work for very large densities. It doesn't work for very small densities. So what exactly is the range of densities where it works? That answer is obtained by us in some self-consistent way, but it's not a very systematic, it's not a standard asymptotic expansion in anything that we know. So that is the difficulty or interest in this problem, is that it actually gives rise to a different method of analysis. We tried to see these series converge, and that convergence is not easy to establish. Okay. So now I want to discuss transfer matrix. Formulation for the same problem. Same problem means for rigid rotors on a line. So I have a line and there are sides with distance A, and at each side there is a rod which is pivoted at the end, and it can rotate freely. So this is theta I plus 1, theta I plus 2. It has an angle of orientation, and each theta I lies between 0 and 2 pi. Okay, and the partition function we said was equal to integral d theta I over 2 pi product over I which is an indicator function, which is 1 if it's an allowed configuration, 0 otherwise, which we wrote as product over ij 1 minus eta ij theta I theta j. Okay, so it depends on the indices I and j and also on the orientation at those indices. Okay, so but this can be formulated in a transfer matrix way like this. So I write ZR plus 1 theta is equal to the partition function of a finite line of length r plus 1, where the leftmost spin is theta and the others are integrated over. And so this is equal to integral d theta prime t theta theta prime zr of theta prime. This is a standard transfer matrix, and this will take value 1 if theta and theta prime are adjacent stuff. They are allowed to they don't overlap, and it is 0 otherwise. So the corresponding eigenvalue problem is lambda f of theta eigenvalue problem. Is integral d theta prime t theta theta prime f theta prime 0 to 2 pi. And now I should solve this for this integral equation where t is given. So what is t? Let us take the case where things can only interact with nearest neighbors for simplicity just now. It's not necessary, but let's use that for, otherwise the transfer matrix is a bit more complicated. Okay, so this is the nearest neighbor transfer matrix. So what is t? Suppose I take some configuration like this here, which is theta, and there is another here, theta prime. So there are two possibilities. One is that theta prime can be just anything and it doesn't overlap, right? That's if the rod is of length L, here you can draw a circle of length L and all orientations are allowed. But there is also a possibility that this thing looks like this, and then not a very good picture. So when I draw this is theta and this is theta prime. There is a range of values of theta prime which is forbidden, and other values are allowed. Okay, so can I determine this range of values of theta prime? That's sort of a high school geometry problem. This length is A, this length is L, this angle is theta, this angle is theta prime. And so what is the value of theta prime if you know two sides and one angle? One can do this with sine law for triangles. So it's easy to get this. And there are two values of theta prime allowed. One is called theta prime lower, one is called theta prime higher. And in this range, you are not allowed, other values are allowed. Then I draw t, theta prime. This is theta prime is the axis. And what happens is that if theta and theta prime lie in this range, then that is not allowed, there is overlap, and all other values, there is no overlap. And the shape of these figures you can easily construct by this construction. And as you vary A, this shape will change. So if A is bigger than 2L, then everything is allowed. So let me draw that because it's useful. So this T looks like this for A bigger than 2L. And then if A becomes less than 2L, you develop some small regions like this. And then when you increase, when you decrease A further, A is equal to 2L minus a little bit, then these things will grow in size. Okay, and I can see what happens as they grow. Okay, but at each point, there is a range of values. Let's call this theta, delta, and minus delta. If theta doesn't lie between minus delta and delta, then there is no overlap. Okay, so now I look at this equation and I see that suppose my theta doesn't lie between minus delta and plus delta. Then I put this in and there is some value of this, so there is some eigenfunction f. So this t is always 1. And the value of this stuff is just integral d theta prime f theta prime 0 to pi, some number. So what I conclude is that f of theta must be of this form, is minus delta and delta. And here it can be anything, but here it is constant. So I have to determine what is this function here. Okay. So now I choose a value of theta here and put this in this equation. Then, I don't want to do the full analysis here. You can do this yourself, but I give you the basic. Yeah. Yeah. T is 1. Yeah. So it gives you a constant answer. When it is in this range, then sometimes it gives you a different answer, 0. So some values are disallowed, and so the value will be less. So the function will be lower than here, something like this, but I don't know the exact shape. Okay, but now I look at this again, and I see there is a range. So this answer can be written in 2 terms. One is where t is 1, and one is where t is not 1, and those you have to subtract. But it turns out then when t is not 1, then f is constant.
Sorry, I mean, all this is being done at 0 temperature or?
No. So this is a hardcore particle. So there is a temperature is not a parameter.
Not a parameter.
Okay. So it turns out that delta f theta
Deepak,
is just some integral.
sorry, Deepak.
Yeah.
So this is still only nearest neighbor, or you,
Right now, for simplicity, I'm working with nearest neighbor. The argument can be extended, but for okay. Yeah. F is constant, not 1, some constant. Okay. So when we are in this range, I put this here in this equation, and it turns out that this can be written as 1 minus some what we call eta of theta theta prime f theta prime. Okay. Now this part 1 is some number, I don't worry about it just now, we'll worry about it later. But the second part is an integral. And it turns out that when you want to do this integral, then f theta prime is constant in that range. So the answer is just simple integral over eta. And so you get the functional form right, but with some coefficient which depends on the amplitude at that place. So, then I just say f is equal to some constant here and it is something else here. And then you can determine those constants self-consistently. So that is the way the answer works. And you can get the exact expression for the eigenvalue. But let me just do this a little bit more formally. So what I will write T equal to 1, 1 minus delta theta, theta prime, where this vector 1 is equal to the constant vector as a function of theta. It's an infinite dimensional matrix, but I just think of it as a long vector with 1. Okay, and delta is the remainder. It is this colored stuff. Delta is non-1 only in this region. Okay, so now, so if I operate T on 1, I will get 1 minus some number times 1 plus some number times delta times 1. So now I take this vector and operate by T again. You know, that's the way to generate the power series. But it turns out, which is where you can easily check, that in this case, delta squared is just 0 from the structure of the T. If you take this T with non-zero elements here and square it, so long as the range is good, the zeros will just multiply and you get exactly 0. So T squared is exactly 0. And so T squared acting on 1 gives you something times 1 plus something times delta times 1. And you never generate anything else. Okay. So only 2 eigenvalues of delta are non-zero, all other eigenvalues are 0. Yes, sir.
Why it is not working? Sorry. So why is the coefficient of something on 1 minus?
The coefficient is 1. I was just, yeah. It depends on normalization of 1. No? Very okay. Okay, so this is the way this works. But you know, you want to extend this further. So now I would like to use the same method, but in 2 dimensions. So in 2 dimensions, I have a row like this. And so this is theta 1, theta 2, theta 3. And this is theta 1 prime, theta 2 prime, theta 3 prime. And there is a T, which is a function of theta I. Theta I prime. Okay, and I want to then solve the eigenvalue equation lambda times psi of theta I is equal to T looks pretty scary on first glance. But you know, so okay, if I do this in the end, what I will get will be ZL, will be some partition function with some value of theta is equal to summation over C alpha okay. But we showed that if the at most one overlap condition holds, then this partition function is exactly given by the partition function of a dimer problem on a lattice of size, length L, width whatever is the original width. And so this is equal to, yes. It's the partition function of some problem like this, where left hand side is fixed to be value theta.
Oh, okay.
And then you
Okay.
kind of transfer matrix structure. Okay, And if you want, you can make a trace by summing over various things. It's not required. Okay. But this is equal to Z dimer of L cross M. Width of this stuff is M, which is equal to summation C tilde alpha something lambda tilde alpha to the power L. It has the same structure. Lambda tilde are the eigenvalues of the dimer problem, transfer matrix of the dimer problem. But there is a discrete number of eigenvalues of the dimer problem because it's a discrete finite dimensional transfer matrix. But these things have to match for all values of L, 0 to infinity. And so all these, you start with the largest eigenvalue, next largest, next largest. And so all these indices must be equal to each other. So more technically, you have to take inverse Laplace transform. And yeah, so there are some complications about inverse Laplace transforms. But so one expects that these eigenvalues are coincident. The set of non-zero eigenvalues of this lambda alpha must be the same as lambda alpha twiddle, which are finite in number. There are only 2 to the power m of them. So then it follows that the transfer matrix for this bigger problem will have at most 2 to the power m non-zero values, and all other values will be 0. And that is true so long as the one overlap condition is satisfied. Once the one overlap condition is not satisfied, this condition, this equal to this, is no longer true, and then the argument doesn't go. In fact, you can check numerically that actually the eigenvalues don't remain 0 anymore. And so this is very funny. Here you have some transfer matrix. Of course, I vary A, and all of a sudden, infinite number of eigenvalues which were 0 before, all of them suddenly become non-zero. It's a mechanism of phase transition which is not studied before. So to that degree, even if you don't like the problem, you think it's a little bit contrived and artificial, then one might want to wonder how this actually happens. And that structure is not fully understood yet, because we are not actually able to handle the case where the AOO condition doesn't hold. Okay. Okay, so the last thing I want to do is in any configuration of rods, on any given site, one particle can overlap at most one other, no more than one. Okay.
Will the problem be different if you have, if you have a discrete set of angles which are allowed in the rotation?
The problem is easier. No, it's much of the structure goes through clearly. See, we are not actually calculating anything in great detail here. Yes.
There is no regime in which that 1 becomes 2, just directly becomes.
Right now, the cases we have studied, it looks like this, but if you study the variations in which you have finite number of orientations, then it's possible that some extra structure can emerge. Maybe that's an interesting way to approach the limit. But now what I want to do is something in the last 10 minutes, is to show that if you calculate using this problem, actually in this problem just now, but again the results are extendable in other cases. If you calculate the one particle density of directions, P of theta. So you have an equilibrium system, you pick a point at random, what is the probability that the direction of that rod is theta? I want to plot this function P of theta. So I showed you some plots before, but now we want to actually, there it was claimed that something happens. And here I want to show that that structure is easy to see. So P of theta is the probability that one randomly picked rod d theta is the rod has orientation between theta and theta plus d theta. This is standard density. And so if I plot P of theta versus theta for A bigger than 2L, you just had uniform, everything is allowed equally likely, there is nothing. Now suppose you make P of theta slightly less, then we are in this AOO regime where I can get the exact eigenvector for the transfer matrix. So I can see right now 1D, but the results are easily extended in higher dimensions, but let us work with 1D for the moment. Okay, so now I have my eigenvector is non-trivial, but what I would like to do, P of theta is equal to, some left and then t to the power I and then delta theta minus theta 0 t to the power L minus I times right eigenvector divided by the partition function. It's a standard definition, and this becomes equal to psi left delta theta minus theta 0 psi right up to normalizations. Okay, but these are known because this one we worked out. It was just constant minus one particular vector. The right hand side was the same, but these two are not identical. One of them is with theta and one of them is with pi minus theta. So this is a product of two terms. Where F2 of theta is equal to F1 of theta plus pi. You have to, by rotational symmetry, you just have to invert the stuff. And so this vector actually looks like this. Sorry. We saw that one eigenvector looks like this. It's a bit less on here and then constant here. That was by operating delta on 1, you got this. Now you will get these extra peaks here because of the second on the left vector. So this is P of theta. I just drew qualitatively. Now I change A. What will happen? These things will become bigger. So this thing will change into this. Like this. And these ends move with A. So what is the end point? Can I tell? That was the largest value at which you can have some, in the delta is this point. So what is the largest overlap, largest angle at which you can have an overlap? That is when these things form an equilateral triangle, L, L, A. Right? So if this angle is delta, I should have cosine delta is equal to A by 2L. So I know the exact position of the endpoint of this wiggly funny curve. The funny curve depends on the details or the shape of the object. But this equation is pretty general. That is the case when there is only one most distant point. Otherwise, you can have X. So anyway, this thing is known. Now, suppose I change A. What happens to this picture? At one point, what happens is very interesting. This graph starts looking like this. This is just a single orientation. So, this T of theta I can calculate explicitly by simple geometry. And then if I look here, then there are two solutions, theta min, theta max, and their width tends to 0, but it tends to 0 as square root epsilon. That is a standard, very robust singularity, which comes from the fact that if you take this orientation to be fixed, then it cuts at two places, but then you vary this angle theta, then this the distance between these 2 points will go as square root. So this function f of theta is equal to square root delta minus theta for theta tending to delta from left. And 0 otherwise on the right. So this singularity is actually a cusp singularity here. So P of theta has a cusp singularity at some point. Otherwise, it's some funny function and it's flat in some region. I can tell that the singularity remains a cusp singularity and its position changes with A, and I can calculate it simply. Okay. All right. So very good. So I evolve this. At one point, it goes into a shape like this, where this left end meets the right end. And then the shape looks like this. Now I go further. As I go further, this AO condition actually breaks. And so the solution is no longer exact, but actually to a very good approximation, this thing still continues to look like this, except what happens is that F1 looks like this and F2 looks like this, and we have to multiply these two functions to get the full solution. Okay, so this product looks like this, here, and there is a cusp singularity, and then it looks like this here. So what was the maximum here at this midpoint is actually becomes a minimum, and you can say two ways. You can say this cusp went like this and came back, or you can say this cusp went through to here and the other cusp crossed it and went to the other side. But all the singularities of the P of theta can be calculated like this, also in higher dimensions. So you can get the qualitative behavior of P of theta by these simple geometrical considerations. Okay, there are extra singularities which occur in P of theta, which I showed you, where P of theta we said behaves like this, and at some other value of A, it became like it became asymmetrical. These symmetry breaking transitions are like the Ising transition. They are not captured by these geometrical considerations. That is not, it's not a geometrical transition, it's an order-disorder transition. There you have to actually analyze the corresponding T, this eigenvalue equation T, and look at the singularities and get the behavior. It can be done, but it is not as straightforward and it requires heavy analysis, and you cannot really get the closed form answers for all things for general shapes. So let me stop here. Yes.
Yeah, unless I missed something, at least in 2 dimensions, somewhere in your parameter space, there should be a sort of standard O2 symmetry breaking transition of the rods. Is that right or not? I mean, quasi breaking.
O2 symmetry breaking occurs actually as soon as I cross the A equal to 2L line. And the P of theta in 2D actually has the same structure. But it has a square lattice symmetry. You know, if you are near the axis, then you have this behavior. This is theta equal to 0. This is theta equal to pi by 2. This is.
Oh, I see. You're saying that you don't lose the fact that the lattice has picked out two directions. It's
Yeah.
always, so it's not, even though the rods themselves live on a circle.
The fact that the lattice is
you don't-
rectangular, you
I mean-
lose the O2 symmetry immediately. But the
I
lattice
see that,
symmetry is
yeah.
there. No, this
Okay,
direction
okay.
is the same.
No,
as
sorry.
this
So I
direction.
just misunderstood that point.
Yeah.
So-
Sumedha, here.
So I just want to clarify something. So supposing you are in this AO phase, like regime, so then you said you can map it to the dimer packing. So as you move across the phase, I mean, is it that the dimer packing fraction changes?
Of course.
It
but-
changes, right?
But the dimer equivalence breaks down. It's not there.
No, if you're within that, you're still within that AO condition.
Then the dimer equivalence is good.
Yeah, and as you move across, you just change the packing fraction, right, of timers.
Yeah. So what happens is that actually, if you look at the dimer partition function, when the AO condition breaks down, nothing happens to the dimer partition function. It continues to behave normally in very simple way. So I had shown some plot like this. This is n as a function of z minus n as a function minus z. Something happens at some large value of z, but we are here and the AO condition breaks down here. Okay. So if you only looked at the dimer partition function, you will not realize that the problem, other problem to which this was equivalent to is no longer equivalent.
The dimers themselves, of course, they don't show any transitions, right?
No, so that is what I had mentioned last time. They don't show a transition if you look at the partition function per site. But there is a percolation transition in the dimer problem, which you can look at if you want.
Okay. That,
No, the partition function per site will not show.
No, I meant the density of dimers in the range of equivalence is small enough that they won't percolate, or it's
Yeah,
big
they
enough?
don't percolate.
Yeah.
They are very low. They is 0.015. The density is only 1.5%.
Yeah.
sorry,
Sorry. No,
one more question was like just from numerics, what is known about this model?
So I showed
in
you
two
some
dimensions.
pictures in the first.
But are there like what are the transitions like it faced?
Yeah, so I had shown a graph, which was, this is L by A. And there are all these horizontal transitions where, you know, it interacts with nothing, interacts with only one neighbor, two neighbors, three neighbors, four neighbors. This is in 2D. And in addition, there are these other transitions where there is a symmetry breaking from pi by 2 across or pi by 4 across and so on and so forth. And in addition, you can also have jamming transitions which are not visible in this plot. You know, some kinetic transitions which equilibrium partition functions don't exactly immediately see. But Monte Carlo, you get this problem. Like if we cannot work with very high densities because the Monte Carlo becomes very slow.
So what about when the pivot point is in the center of the rod?
Sorry?
The pivot point is the center of the rod.
So that we have studied numerically. I showed you in the first lecture that the AO condition never works, but there is an equivalence to a problem which looks like polydispersed rods on a lattice. That equivalence is still there.
And the P theta is same.
P theta looks the same qualitatively.
Yeah, so this is related to just not this one, but the question that you are summing over a class of configurations.
Yeah.
To get the partition function, but
Yes.
they are all connected to each other through some kind of a kinetics, or?
Right now we didn't discuss any kinetics, but
Yeah,
you
no,
can
I understand.
certainly say that theta can vary continuously and then you impose some kinetics.
Mhm.
And yeah, so as of now, the models we have studied, you can actually make all the rods parallel in some place and then rotate them together into some other direction and so on and so forth. So it looks like they can be varied from any configuration to any configuration. I have not shown this by it seems quite clear that it will happen.
Hard systems, there are sometimes, you know.
Yeah. And so that is not here just now. Because at least these models were thin rods. If there are thick rods, then what you are saying might very well happen or will happen.
So Deepak, can I ask one clarification? You said the jamming transition, it is seen only in the simulation. So is it there in the model or it's not there?
So the partition functions may not always be able to see the jamming transition. But, maybe they can see it. That question has not been theoretically settled. But if they do see it, then we have not reached, we cannot, all the AO condition breaks down long before that case is reached. So while the model continues to be interesting beyond the regime where it is more tractable, there is not too much I can say analytically about that. And near the jamming, we cannot say numerically either because the jamming is a tough problem, numerically even. Percolation transition occurs much before and seems quite tractable, but doesn't seem to have been discussed. Okay.
The partition function, do you see any?
No, we don't see anything. So, of dimers. Suppose you take dimer model with but I can just ask what happens in the dimer model. And I'm saying that there will be a percolation transition and Leib theorem will continue to be valid. And so the partition function as a function of Z will not see anything at the transition point. Okay. It is like that you take this Ising model in 3D. There is a percolation transition of oppositely oriented spins, but the Ising model partition function doesn't see this percolation transition. Okay. Because it depends on the definition of what is a cluster, and if two things are adjacent like these, do they count as one cluster or not? That changes the location of the percolation transition. So the definition of the percolation transition depends on what you call clusters, and that is outside the definition of the Ising model by itself.
Okay, thank you, Deepak.
Okay.